Hello and welcome to Morko-Engineering. My name is Eki Lehtimäki. I thought I would share with you a presentation that I had some time ago at the World Summit on Digital Built Environment. The presentation is called The Importance of Human Thinking in the Era of Algorithm-Aided Structural Engineering. It got very good feedback from the audience in that particular summit, and people were quite excited about it. But then again, I don't think enough people had the chance to see it there. Not everyone was able to travel to Helsinki that September, and also not everyone who traveled there was able to attend this particular session because there were different parallel sessions going on in different rooms at the World Summit on Digital Environment. And it's definitely worth for more people to see this presentation. The topic is importance of human thinking in the era of algorithm-aided structural engineering. We're definitely talking about algorithms and algorithm-aided engineering here, but we will heavily concentrate on the human side of things, which I think is way more important than the computer side of things and algorithm side of things. Let's take a look at it. So first of all, about me, my name is Eki Lehtimäki. I'm the CEO and founder of Morko-Engineering, the company, and Morko-Engineering's been founded 2018, so we've been in business for a while now. And what we do is mainly structural engineering, the regular kind structural engineering, and we offer learning services for other engineering companies. So any engineering related learning, either live or online. We have our own online learning service called Morko Learning. You should check it out if you haven't already. But then alongside that, I'm developing my own software for algorithm-aided structural engineering. It's called Teräspertti. And the main purpose of Teräspertti is not to be selling it to other companies or even to be consulting with it. It's mainly aimed to allow Morko-Engineering to be a way better engineering company and offer better engineering service to our clients in the future, and to be to have a leading role in the transformation towards algorithm-aided structural engineering. So for clients, we offer structural engineering services and learning services, and the algorithms, whatever they do, doing it on the background. At the WDBE World Summit on Digital Built Environment, I don't think everyone in the audience was a structural engineer. There were lots of other digitalization-oriented people from the construction industry there. So I needed to simplify things a little bit, and I presented the structural engineering workflow, an oversimplified version of it, as a waterfall model. So you can have opinions on waterfall models, but it's a very good way to oversimplify a process, and that's what I did with this diagram in the summit. So engineering process of perhaps a power plant boiler, steel frame or boiler building structure, or any other industrial steel structure would probably go something like this. There's a pre-engineering phase for earlier design. There's mainframe basic engineering stage where the more detailed actual basic design of the structure is done. Then the structure is divided into tires that are constructed separately, and there's a detailing phase. Typically for each of the tires there's a separate detailing phase which follow each other as the construction goes on. And then there's a documentation or drawing creation phase for each of the tires, often separately, because that fits the overall schedule of the project better. Now, at the digitalization seminar, there were definitely some people present who don't like to talk about paper drawings anymore. So I just wanted to mention that the communication of the design information does not have to be paper drawings. That's important to mention when we're talking about digital built environment. But there is definitely some sort of communication phase where the design information is communicated to either the construction site or the workshop if the structure is prefabricated. Now, the beginning of this process does not have any raw material going on. So industrial process maybe has some raw material going on, but the design or engineering process of a construction is definitely a thinking process. There's only brain power going in as raw material, and then at the end of the process, there's not a single client who will order the project. Instead, there's a whole ecosystem of multiple stakeholders of the construction project, and all those stakeholders have an organization, and there's people in the stakeholders organization for every single stakeholder. All those people have some knowledge in their heads. They know their own stuff much better than the engineer here knows. And they need to be able to communicate that knowledge back to the design process or the engineering process, and that knowledge needs to flow up the waterfall model. If you are familiar with the waterfall, you will know that information flowing down a waterfall is relatively easy, but flowing up a waterfall or flowing up of information in any kind of process is typically very, very hard. It's much harder, and when we have engineering process problems, they usually have something to do with the flowing up of information. Now let's talk about the algorithms for a little bit, and I'll talk about Teräspertti, our own algorithm software. I'll illustrate it using the same waterfall diagram that we just looked at. So in the beginning, in the blue phase, pre-engineering phase of the design process, human designers are mainly thinking about the blue things, the pre-engineering things, while they are also hopefully, and I underline hopefully, communicating with all the other stakeholders, visualizing the design outcome, and trying to achieve a common understanding with all the other stakeholders, because the pre-engineering, the blue phase, is where we make all the big decisions, although we haven't spent that much design time yet on it. Now, if we have the possibility to use algorithm-aided engineering, such as Teräspertti, humans can be thinking about the overall topology of the structure, like the supporting of the actual boiler, which is the main purpose of the boiler building we are looking at here. Supporting of the boiler, and also some very important technical issue, such as seismic design of the structure. So very often, if it's a seismic building in a seismic area, the most important part in the pre-engineering is achieving working solution for the seismic design of the building. It doesn't have to be final, but we need to have an excellent strategy of how we are going to handle the seismic problems of this project, and that's important task in the pre-engineering phase. Now, while the humans are thinking about this stuff, the blue stuff, pre-engineering stuff, algorithms can already be running a loop on the other things, the basic engineering, the detailing, and the workshop drawing phase. So algorithms can be doing the red thinking about main platform beam topologies and the platforms and stuff like that. That's important for the building, but maybe not in the pre-engineering phase yet. Algorithms can already be running on the green things, the detailing things, so connection details, that sort of thing. And algorithms can already be running on making the documents, so that we will have details and we will have overall design where automatic drawing creation works as well as possible, so that it saves human labor in the process. So that's the idea of pre-engineering algorithm-aided design. Algorithms can produce information about the rest of the design process semi-automatically, while humans are mainly thinking about the blue things and communicating the design to all the stakeholders, visualizing it with the aid of algorithms, and trying to achieve a common understanding with everyone else in the project. Now let's look at the red phase, the basic engineering phase of the main. Now the pre-engineering is already done, and now humans are thinking about the red things. Humans are thinking the basic design of the structure, platforms, platform beams, calculation models, and already maybe producing calculation reports. And they have to be producing calculation reports so that they can communicate the results to everyone else in the project. Now there's Teraspertti user interface, which is here controlling the three others. So Teraspertti at the same time is running, or the algorithms are running on the detailing things, maybe connection detailing and other details, and then they are running on the orange things, the automatic document creation. Now let's go to the detailing phase. Now in the detailing phase, it's very important for humans to be thinking about the details. In the previous stages, they were made quite automatically by algorithms, by Teraspertti, but now we need to actually design all the details. Many of the details we can use the automatic ones, but then we need the human brain power to solve the things that algorithms couldn't solve in the previous stages, or where algorithms seem to be going wrong. And then algorithms can still be running on automatic drawing creation, making sure that when we reach the orange stage of the building, of the process, there's not much for humans to do. All the drawings, all the documents could be as automatic as possible. So in the documentation stage, humans are thinking about drawing creation, document creation, and hopefully they don't have much to think about. Everything's already been automatically documented before. Or to say that better, all the automatic algorithms that are creating the documents are working properly so that humans can create the documents as automatically as possible in this stage. Not fully automatically, some things always need to be fixed by hand, but the amount of that stuff should be as small as possible if we want to get some advantage from the algorithms we've been using all the time. So that was about algorithms. Let's next talk about humans. So what are humans good at? We already learned that algorithms are good at repeating simple design procedures over and over and over again, tirelessly, thousands and thousands of times, relatively quickly. And algorithms are very good at making documents automatically, at least some kind of documents. Maybe if they're too complicated, humans need to fix something, but algorithms can make quite good documents quite automatically. Now human brain is very good at, or humans are very good at communicating things, important things, to other human beings. And I've been using a red communicator symbol here to illustrate this stuff. And humans are very good at teamwork. Humans are very good at managing other humans, especially some people are. Now humans are also good at understanding complex and abstract things. Algorithms can make complex mathematical operations, for example, but they don't really understand what they are doing. They're just high-speed idiots, and that's why I need humans who actually understand the complex and abstract things very well and understand what they are doing the analytical analysis for. And they are good at simplifying complex problems into a series of less complex sub-problems. So simplifying things that are complex into a series of solvable sub-problems. This is what the bluish thinker symbol here stands for in my next few slides. Now there's a code writer symbol here, a purple one. Humans are good at writing code and designing algorithms. And then humans are good at the same thing that algorithms were. They can repeat simple design procedures, maybe not as fast as the algorithm, but they have a little bit more understanding about it. And they can definitely repeat simple design procedures, and they've been doing it in engineering companies for a very long time now. And they can make documents, and they can make documents that that are not automatically made, and they don't need to be checked as the same way automatic document creation needs to be checked. So this is what humans are good at, this is what algorithms are good at, and it's partly overlapping. Now, in the traditional engineering business, I underline this is the traditional way of making things. And here are all the stakeholders. They also have some communication guy, and the engineering company definitely has one team leader or project manager whose job generally would be mainly communicating towards the stakeholders. And then there needs to be the brainy guy who will, especially in the pre-engineering and mainframe basic engineering, do the actual thinking part of the engineering work. Now, in the pre-engineering, they can probably work just the two of them. In the mainframe basic engineering, there's more stuff to do. Like if you're working in 3D models, there's more modeling work to do. Relatively simple engineering tasks that just need lots of hands to do it, so that it can be done within the schedule and not late. So maybe a couple of heavy lifters to help these project management and thinking people in the basic engineering phase. The pre-engineering with simpler models and simpler documentation maybe could be done by the two. Now maybe we need 4 in the basic engineering. In the detailing phase, we are closer to the deadline, and there's way more stuff to do because there are thousands and thousands of details, many of them relatively simple. So we can add more people to the project, and they can be working on different details and very well managed and organized, because we have the project management guy here who is communicating to the stakeholders but also to his own team, his or hers. And then in the drawing creation phase or documentation phase of the project, we are now a week or 2 from the deadline, so very likely we are needing lots of hands to make all the documents in the traditional engineering way of things. So to show this another way, again an oversimplified way of describing the project management or the management of engineering business, the business perspective of the engineering would be a resource allocation diagram. So I have time here on the horizontal axis. There's the pre-engineering phase and how much time that needs, the basic engineering. There's detailing and documentation of the first tier of the building, detailing and drawing creation of the second tier, the third tier, and so on. And then there's the construction phase of the project, and there's people on the vertical axis. And the project management or the communication guy definitely will be part of the project team throughout, also in the construction phase, because definitely the construction site or the manufacturing workshop who prefabricates the structures will need to be able to communicate with the designer even in the erection or construction phase. So the manager definitely is from the start to the end. Also, a thinker guy, she or he will have lots to do in the early stage of the project, and maybe less, but definitely will be an important person in the detailing and documentation phase, and probably, especially if there are any changes in the construction or anything that couldn't be predicted, the analysis guy will be important person of the team even in the construction phase of the project. But then the green and orange skills, the detailing skills and the documentation skills, they are mainly needed in the detailing and documentation phase of the project. So there's way more people, much bigger project team in the middle of the project lifespan, and in the beginning of the engineering work and in the end of the engineering work, the team is much smaller. Now, this was supposed to be the business perspective of things. So when we're talking about business, we're talking about money. All these people need to be paid salaries, and the cost structure of the engineering company who does this is mainly a box. So time multiplied by the amount of people and the salaries of those people who are working in the company is the cost structure of the company. Now one could argue that even if the cost structure of the company is the people's amount and salaries multiplied by time, they are actually creating value to the project only when they are working on the project. So their work or the cost is valuable only when they are working on the project, and the rest in traditional engineering business perspective would be considered waste. So we have value, we have waste, and we have the cost structure. Now to reduce this waste and to get rid of the waste, the company would be tempted to sell more projects. There would be a project N, which is our project that we just looked, and they would have a previous earlier project M, that the same green people were working, but then there's an added second project manager and the second analysis person who are working on the project M, and then there's a blue and red guy working on project N, and maybe the same green guys are allocated to both projects at different times. And then there needs to be yet another project to get rid of this waste. So to get this balanced, they need to be selling more projects. Now, these people maybe don't have overlapped because the process is optimized for them, but this blue guy and red guy have an overlap here. They are need to be spreading their time between multiple projects, the end of the project M and beginning of project O, and that will eventually make them angry. I have the angry face symbols here to represent. We have a conflict there. We've been optimizing one resource, and at the same time we've been overbooking the second resource, and we've been making the second resource quite angry. Now that's not enough. We still have some waste left here because we are not working in the detailing phase with the same amount of people as in the drawing phase. So maybe we saw the process a little bit, making it a little bit more effective. 2 guys are leaving, and then we have overbooked people here too. It looks very effective because we are using the resources optimally, but some of the people are getting angry because they are not working the way that would be comfortable for them. So we have more angry people here in the organization. Now, everything was based on a schedule that had deadlines that were decided beforehand. Now, sometimes projects go wrong, timetables and schedules are changed, deadlines are moved, and if we've booked the resources too tightly, we will have overlap here with the green people also. And this type of change will break everything. We will get all the faces here angry faces. Now, if we have too many angry faces, people will start leaving our company. We just cannot handle too many angry faces. They will think that maybe the competitor's organization is better, and they will leave. Now, unfortunately, the competitors have their own problems. They have exactly the same problem because they are using exactly the same business model. So they have their own angry people, and those angry people are leaving the company also. And then we end up in a situation where there's just angry people going round and round from company to company, and each company is equally shit, and we are just covered in angry faces. And this, in my opinion, is the way to fuck up an entire industry. Now, my goal here is not to teach you how to fuck up an entire industry. Instead, my goal is to teach you how to do quite the opposite. So let's next take a look at the algorithm times of engineering. So in the algorithm-aided engineering process, you still need your red communicator, team leader person in your team. You still need your blue analytical thinker guy in your team. But much of the heavy lifting in the detailing and documentation phase of the project can now be done almost automatically by algorithms. So for the green and the orange phase, you might need just a little fewer people and more algorithms. You need someone to write the code for the algorithms and be running them. That's the purple guy. And probably you still need a few green guys to do manually some of the stuff that the algorithms couldn't handle, even though they tried. Now, much of the writing of the algorithms must happen before the busiest detailing phase of the project. You cannot wait until the busiest time starts and then start writing the algorithms. You write the algorithms beforehand. And that changes business-wise, I think, the engineering process quite a bit, because the time outside the busy project phase is no longer considered waste. Instead, it's value creation time, and the project time is called value cashing out time. Value is created outside the busiest project phase, and value is cashed out in the busiest project phase. There's a separation in time between these two times, and that changes everything, because extra time is no longer considered extra waste. Instead, time now equals time for additional value, time equals flexibility, time equals resilience, agility, and time equals freedom. And in the industry side, that might just change everything, so that no longer you will have the angry faces. Instead, you will have happy faces in your organization and everyone else's organization. And this is the happy future we are aiming for. So it brings me to the summary of my presentation. First of all, my 3 points. First point, Morko Engineering is a good company. Second point, Teräspertti is a good software for algorithm-aided structural engineering. But my third point is that engineering today is quite a troublesome industry, and algorithms by themselves won't help much with any of that trouble. Instead, it's the people who are applying the algorithms who possess the power to either reduce trouble or generate more trouble. And moreover, it's the managers who manage the people who apply the algorithms who possess this power, either generating more trouble or reducing trouble. And that's why we need to be wise, and we need to be aiming for happier times. We need to be aiming for the happy faces. Thank you for your attention. This was my presentation for some time back at the World Summit of Digital Built Environment. My name is Eki Lehtimäki, the CEO and founder of Morko Engineering, and I will see you later for some other topic. Goodbye.